everyone, welcome back to mahasarkar.co.in. In today's video, we are going to learn about total energy of particle performing simple harmonic motion. Before learning this article, if you remember, we have learned the differential equation of SHM, we have gone through acceleration, velocity and displacement of particle performing linear simple harmonic motion. So, we'll just write the few things. If suppose m is the mass of particle performing simple harmonic motion. M is what? Mass of particle performing simple harmonic motion with velocity v. So if v is the velocity of particle in SHM, then if you remember, we know the value of velocity, that is equals to what? Omega in root a square minus x square, where omega is angular frequency. Omega is what? Angular frequency. A is amplitude of SHM. A is at amplitude and x is the displacement at any instant. Displacement at given instant, at any instant. Okay. Now we again know that if particle is performing simple harmonic motion, its potential energy converted into kinetic energy, then again kinetic energy converted into potential energy. So we have to consider both the forms of energy. So we are going to find out first kinetic energy of particle in SHM. So see, suppose we have particle of mass m with moving with velocity v, then kinetic energy can be given as by formula. Basic formula is what? Half of mv square. What is v? Omega in root a square minus x square, and therefore v square equal to omega square into a square minus x square can be the formula. So just substitute this formula. So it is like half of m into omega square into a square minus x square. You know that what is m into omega square? It is the force constant. So equal to half of k into a square minus x square. This will be the formula for kinetic energy of particle performing linear simple harmonic motion. Say this is equation capital A. Now to find the potential energy, we are going to consider the work done, because we know that. First I will just give the title potential energy of particle in SHM. Potential energy of particle in SHM. Now just imagine the case of simple pendulum. Simple pendulum is at mean position, going to the extreme position, again coming back to the mean position, again going to the another extreme position and coming back. So if I trace the path of that, say this is mean position O, it is going towards the left, it is going towards the left, say at up to point A, and again to the mean position I am going towards the right side up to point B. So consider any instant P where the displacement of the particle is x. So if I write all those things, so let P be the position of particle, P be the position of particle at distance x, at instant t. Okay, P is the position of particle at distance x and at instant what? T. Now say particle moves from point P to point Q. Before that, what is important factor? If particle is at point P, still restoring force is acting there. Restoring force always acts towards which position? Mean position. Restoring force, if it is acting towards the mean position, then I can write by definition restoring force acting on particle, restoring force acting on particle is given by F equal to minus k into x. So this is equation number 1. Okay. Now If I move the particle further by small displacement dx, if I change the position of particle from P to Q, so how much force is acting at point P? This much of force is acting. If I move it from point P to Q, then again I need to apply this much of force. So I will write the things. Let the particle is displaced through infinitesimal small value dx against force F. Okay. So if force is applied and displacement is done, then what is done in the practical form? I will say work done. Then the work done during the system. How to write the work done? Then work done dW equal to force into displacement. I will say it is minus. Why minus? See, force acting towards the mean position and you are performing the displacement in opposite direction. So basically work done should be what? Minus. So substituting value from equation 1, equation 2 this one is. Therefore from equation 1, work done dW can be equal to minus of minus kx into dx. Minus minus will be what? Positive, so we will get kx into dx. This is the work done. So this is equation number 3. This is the small work done while moving particle from P to Q. If I further it move from Q to R, then same amount of work will be done. So say I consider the particle is totally changed its position from x equal to 0 to x equal to x. Okay. Its total displacement is taking place from what? 0 to x. So I can find total work done during x equal to 0 to x equal to x can be written as w equal to integral of dw from x equal to 0 to x equal to x. So it is like 0 to x of x into dx. It's simple formula. You are well familiar with the formula for integration. Power is 1. Integration of x raised to n ka formula. X raised to 1 plus 1 becomes 2 divided by 2. Okay, sorry. I have written directly. One term I forgot. See, it is kx into dx, x equal to 0 to x. So k will be constant from 0 to x. Variable is same, so values will not change. So it will be like half of k into x square. This will be the work done. This will be the work done. Okay. Now we know that amount of work done is nothing but what? The change in the potential energy or the potential energy. This work is stored in the form of potential energy. Therefore, potential energy of particle equal to half of k into x square. So this is equation B. Now we have got two formulae. First formula is for potential energy of particle, kinetic energy of particle given by equation A, and second formula given by equation B. Now total energy of particle performing SHM is, how to get the total energy? Total energy is equals to what? Sum of kinetic energy plus potential energy. See, substituting the value of kinetic energy, half of k into a square minus x square plus half of k into x square. Half k common, a square minus x square plus x square. Minus x plus x cancel, so half of k into a square. This will be which energy? Total energy. But what is value of k? Then I can replace the value of k here as what? M omega square. So it is equals to half of, so I will write in short E equal to half of m omega square into a square. This is the formula for total energy of particle performing linear simple harmonic motion. But again, if you remember, omega is equals to what? 2 pi n. N is frequency. So I can get E equal to half m. Square of this means what? 4 pi square n square a square. So if mass of particle is constant and all these things are constant, then I can say energy or total energy in SHM is first directly proportional to n square, second directly proportional to a square. If mass is also changing, then it's directly proportional to mass also. So this is the term in which we can find the potential energy. You can show that the total energy of particle performing linear simple harmonic motion at all the point is always constant. Better you try that. It's very simple. You just need to put the values of x as equals to 0 and x equal to 1 at both the position, like mean position and extreme position. So this is the article for you. I hope you understood this article. Thanks for watching mahasarkar.co.in. Have a nice day.